Hey everybody, Dr. A here, and in this video we're going to be exploring another example dealing with three-dimensional Cartesian vectors. So let's go ahead and get started. In the given information, we're being asked to express the force F as a Cartesian vector and to determine its coordinate direction angles. So let's go ahead and take a look at the figure we're given. Here we have our XYZ axes, so this is a three-dimensional system here. We've got our positive x-axis here. We have our positive y-axis heading in this direction. We have our positive z-axis coming up here. Now, if you notice, we have some of the negative axes here showing as well. So we have our negative y-axis coming off to the left side, and we have a negative z-axis coming down here. Now, the reason why this is important is because our given force, which is 300 kilonewtons, is acting in three dimensions in the octant that has a negative z component. So if you notice, this force vector F, it's going to have a positive y component, a positive x component, but a negative z component. And you can tell that because it's tilted at this 45-degree angle below the xy plane. Now, its shadow or its projection is being cast in the xy plane, and its projection has a 30-degree angle from the positive y-axis. So if you look back in your notes, or if you look at a couple of previous videos when we had some background information on this, you can tell that the way this vector is being expressed in 3D is by its projection angles. So we sometimes call these theta and phi. So this 30-degree angle and this 45-degree angle are not really meant to be thought of as coordinate direction angles, but they are thought of as these projection angles because they come from projecting this vector F into one particular plane, in this case the xy plane, and then decomposing it into its three components from there, okay? So how do we analyze a system when we have these projection angles instead of coordinate direction angles? Well, again, look back in your notes and look back into a previous background video, but the way we do this is we look at each of these projections as a two-dimensional or planar right triangle. So here's the first thing I'm going to do to look at this. I'm going to say, okay, this force vector F that has a magnitude of 300 kilonewtons, it is casting a shadow or a projection up to the xy plane, and this segment is its projection. So I'm going to go ahead and give that segment a little vector arrowhead there, and I'm going to call that F prime, all right? And so what I'm going to do is I'm going to say solution, and the first thing I'm going to look at is a two-dimensional view of this vector that I'm given, its vertical projection, and its shadow or its projected value in the xy plane. And so when I look at that as a two-dimensional triangle, what am I going to see? Well, I can draw this like so. Here is F right here. F equals 300 kilonewtons. And here is its shadow or its projection, F prime. And then I've got this little z component here. Now, this is forming a right triangle. Now, where is this 45-degree angle that showed up in our original figure? Well, that 45-degree angle is this angle right here, 45 degrees. And so what I can do now is use basic right triangle trigonometry to decompose this magnitude of 300 kilonewtons into some components. Now, here's what's interesting about this. This dashed line right here, this dashed segment of this triangle represents F sub z, okay? That's the z component. So I can write this as F sub z. So if I do some basic right triangle trigonometry, what am I going to get? Well, I can say F prime is equal to 300 kilonewtons times what? Well, you can say that that's times the cosine of that 45-degree angle. And then, of course, we can say the z component, F sub z, is equal to that 300 kilonewtons also times the sine of that 45-degree angle, in which case, sine of 45 is the same thing as cosine of 45. So I'm going to punch that in my calculator and say, 300 times the sine of 45 degrees. And, for both of these, what I get is 212.1 kilonewtons, okay? So 212.1 kilonewtons. And we just want to make sure that we're being careful here, especially with a z component. Why? Well, we said that this vector f is pointing in the negative z direction, so really we need to have a negative sign in front of the z component calculation, okay? Now, I do want to make a note here. We want to make a little quick note. This figure, I just drew it quickly freehand. This is not to scale. Remember, it's a 45-degree angle, which really means that f prime and fz should be drawn at the same scale or to the same length, which I didn't really do that very well here, but that is the case, okay? Now, what are we going to do? Well, the next thing we want to do is get the y and x components, right? So what I'm going to do is I'm going to look at this other two-dimensional triangle in the xy plane, okay? And so what happens when I look at this other second two-dimensional triangle that's in the xy plane? Well, its hypotenuse is going to be f prime that I just calculated, okay? So I'm going to get this f prime. I'm going to draw this a little bit better for us right here. So this is f prime. And what else am I going to be able to see? Well, I've got these dimensions like this that form a right triangle, okay? And so what are these dimensions going to represent? Well, this dimension I'm showing here, that of course is the y component, fy, and this dimension over here is the x component, fx. And so again, how am I visualizing in this? Well, this fx is this leg of this right triangle, and then this fy right here is this leg of that same right triangle. And where is that 30-degree angle? Well, that is just right here. So again, what am I doing? I'm taking this three-dimensional figure that I was given here in the problem statement, and I'm breaking it down to two accompanying two-dimensional right triangles, okay? So now what I'm going to do is I'm still going to be using some right triangle trigonometry here. So I can say that fx is going to be equal to f prime times the sine of that 30-degree angle. And of course, we know f prime is the 212.1 kilonewtons, and we say times sine of 30 degrees, which of course sine of 30 degrees is just 0.5. So I'll get 106.1 kilonewtons, and then the y component is going to be f prime times the cosine of 30 degrees. So that again is just that 212.1 kilonewtons, again times cosine 30 degrees. So let's see what that comes out to be. We get 183.7 kilonewtons for that y component. So I'm almost done, okay? I've got, each one of these components. I've got the z component first, and then I got the x and the y component. So where does this shadow or projected component come from, f prime? Well, again, I projected f into the xy plane, and I call that projection f prime, and then I used f prime to help me get fx and fy, all right? So as a Cartesian vector, how is this going to come out? We're going to get f vector equals fxi plus fyj plus fzk, and I know those components, right? So I get 106.1 I, and then plus 183.7 J, and then minus 212.1 K. And then we can kind of bundle up our units off to the side in brackets as kilonewtons, or you can write those kilonewtons next to the each of the individual values, the 101.6, 183.7, etc. Okay, so this right here is pretty much our answer. Okay, but the problem also asked for the coordinate direction angles, and so if we again look back into some previous content or your notes, how do I get those coordinate direction angles? Well, we say cosine of alpha is equal to fx over magnitude of f. And so I can take that as 106.1 kilonewtons divided by the magnitude of f, which was given at the very beginning, right? That's the 300 kilonewtons. So we say divided by 300 kilonewtons, and that gives me a decimal, so 106.1 divided by 300, that gives me a value 0.3537, and then I take the arc cosine or the inverse cosine of that value, and I get 69.3 degrees. And then I'm going to do something similar with the other coordinate direction angles. Cosine of beta is Fy over the magnitude of F. And so that's just going to be 183.7 kilonewtons over 300 kilonewtons. And let's punch that in our calculators. 183.7 divided by 300. And then arc cosine of that. And so for beta, I get 52.2 degrees. And then similarly, I can get cosine of gamma is F sub z over the magnitude of F. And so I'm just going to kind of skip an intermediate step here, and I'm going to go straight to my final answer. So remember, for F sub z, you have to include that negative in the negative 212.1, okay? So make sure you include that negative in your arc cosine operation, and you should get 135 degrees here, okay? And these are your coordinate direction angles. And so all of that collectively is the solution to this problem. If you wanted to resketch this vector and show the coordinate direction angles, we can. And the thing you would need to remember is where these coordinate direction angles are measured. They have specific measurements, right? So alpha is always measured from what? From the positive x-axis to the vector. Beta is always measured from the positive y-axis to the vector, and gamma is always measured from the positive z-axis to the vector, okay? And the fact that gamma came out to be greater than 90 degrees, it came out as 135, means that you're sweeping through one octant into another. So it shows that we're going from an octant with the positive z component down into an octant that's not more than 90 degrees away, into an octant with a negative z component. Okay, so hopefully you found this example helpful. If you did, please hit like and subscribe, and be on the lookout for other examples and other videos like this. Thanks for watching.